Morning, everyone. So our first section in this course here is to introduce some of the math that we're going to be seeing throughout the rest of the course. The goal today is to, when given a formula, we may not have much understanding with what the formula is trying to derive. However, when faced with sort of an equation, we want to make sure we're okay practicing isolating for variables, solving, evaluating for numbers, and sort of developing this sort of mathematical toolkit that'll be useful for the remainder of the course. So I'd encourage you to actually have out a piece of note paper yourself, copy down the questions as we do them. In fact, after we write down the question here, you can even pause the video, try it out for yourself, and then when you unpause the video, you can compare with how we did so far. So we'll start off here. Let's take a look at taking an equation and just doing a solve sort of operation. Solve essentially means, so we have a formula from our formula sheet here. We have an equation which gives you a relationship between different variables. When it says solve, you're basically isolating for a certain variable. So for example here, let's start off with the equation here. V is equal to d over t. You might remember that in your earlier science classes here. This does have to do with speed is equal to distance divided by time. In this section here, we're just interested in doing the isolating part. In this case, I want you to solve or isolate for t. Meaning, even though we already have the function here, we have t in the equation, when it says isolate for t, I want it to be t equals something. So let's just practice doing this isolation here. The t that I want happens to be in the denominator, right? This is a divide. What I want to do is I want to multiply both sides by t, right? Algebra says if you do the same thing to both sides, you keep the equality the same. You don't normally need to write what's in the red there, but I'm just showing you sort of all my steps here. When I have a divide t and a multiply t, the t's cancel out. Now we picked up the t term on the left side. Now we're closer. We have v times t equals to d. All I need to do is get rid of the v term. And all we're going to do, the opposite of a multiply is a divide. Let's divide the v back over. And we end up getting t is equal to d over v. All right. So that's sort of isolating or solving for t. We now have the expression t equals the distance divided by the speed. It essentially is the same formula, but because we've isolated for a different variable, if we're given d and v, we can just simply plug it straight into this manipulation of it, and we got the time. For a very simple expression like this, some of you may have learned this sort of triangle pyramid just as a memory aid here. Let's go back to this formula here. V is equal to d over t. You would actually write out this almost like a pyramid. You would say V is equal to d over t. And essentially what it does here is if I use my finger and I just sort of cover over the V temporarily, if you want to find the V, that's just going to be distance divided by time. So far in this section here, we're interested in finding the t. So I imagine covering over the t is going to be distance divided by velocity. And in a similar fashion here, if I wanted to find the distance, if I temporarily just hover over the d here, it's going to be given by v times t. So for a very simple expression here, which just three variables in this relationship, this triangle here gives you a nice sort of memory aid with doing the isolations. We're going to see with the upcoming questions, the second that the formula gets a little more challenging, you can no longer use this triangle. So we really do need to be comfortable with the algebra here. Even if I was given numbers, here's the d, here's the v, I would usually just isolate it through, just play around with the variables, and then in the end, I just punch in the numbers afterwards. So let's try out another expression here. Again, we're going to come to these expressions later on in the course. So I have here mgh is equal to 1/2 mv squared. And in this case here, I want to solve for v. So no numbers have been given. All I want you to do is I want you to see if you can rearrange this expression here and see if you can have v equals something in the end. So just keep an eye on where our target is. In this case here, v is actually on the right-hand side. Whatever is not v, I want to kick over to the left side. So the first thing that I notice here is I notice that it's v squared, it's being multiplied by m. In fact, this multiply m happens on both sides. The opposite operation of multiply by m is going to be a divide by m. Again, later I'm not going to show you this step, but once you divide by m here, the m actually kills off the m on both sides, leaving you with a slightly simpler expression here. G times h is equal to 1/2 times v squared. So now we're a little bit closer. Nicely, the masses ended up dropping out. The m's dropped out. And now all we need to do is we need to slowly just drag the numbers over to the left side. In this case here, we actually have a 1/2 being multiplied by v squared. You could think about, well, opposite of multiply is a divide, but in this case here, what we need to divide by is actually divide by 1/2. Dividing by a fraction is a little more strange. Is there another way I can get rid of the 1/2? Well, since this is in half, what I can do is I can actually take a times 2 on both sides here. I know divide by half actually ends up as a multiply by 2. The multiply by 2 will cancel out this half on this side, and I'm going to now have the expression 2 times gh is now equal to v squared. And finally, when you want to find v, this is v multiplied by itself when it's squared. To get rid of that operation, I need to take square roots of both sides here. I now need to have square root of 2gh. This has been solved for v. I've been saying I want v equals something. Even if the v is on the right hand side here, I want you to know here, because this is an equality, we're saying the v is equal to root 2gh. So as long as they give you what g is, what h is later on, you can very simply punch your way in for v. Yes, every time you take a square root, it actually does give you the positive and negative root here. In the physics, in our interpretation of this one here, let's say v ends up being speed, because speed is what's going to be called a scalar. Speed is always going to be positive. I'm just going to take the positive root. So somehow the math actually gives you more than one answer, but our physics is going to come back and actually going to help us decide, do we want one root or the other root? So a little bit harder equation now. I'm going to give you the relationship t is equal to 2 pi, the square root of L over G. Right. In this case here, I want you to solve for L. Right. So again, see if you can play around with this equation. You see that the function itself is a lot more challenging, so you can't just draw a simple triangle, but we'll just work our algebra through. We want to get our target here, which is L. I want the whole relationship expressed as L equals something. Sometimes this is not possible. Sometimes writing it out explicitly here is very hard, but so far in the functions I've given you, you should be able to just kick everything over to the other side. In this case here, I actually introduced to you pi as a constant. Pi is by definition the circumference divided by the diameter. I know it's an irrational number, 3.14, and a whole bunch of numbers afterwards. Most of your calculators here will have the pi button as a constant, and all we're going to do here is we're going to treat that as a number, and then anytime you wanted to type a decimal, you just go 2 times that constant in your calculator. That would give you a little bit over 6. In this case here, I'm just going to leave pi as just a placeholder for a number. Treating that as a number, I have 2 times pi times this root L over G. First thing that I can do is I can bring the 2 pi over to the left-hand side. Right now the 2 pi is being multiplied, so I'm going to go t divided by 2 pi. That's equal to root L over G. That's the easiest thing to drag over. Next thing I want to operate on here is I want to get it out of the square root, get it out of this house here. So to do the opposite of a square root, we need to square both sides. Upon squaring both sides here, we're going to actually have t over 2 pi, all squared. If I square a square root, I'm going to just have canceled out that square root there. Now I'm super close here. I end up with L. In fact, in this case here, this t over 2 pi squared here looks a little more confusing. If you like, you can actually just square the numbers inside. So because this is a fraction, the top term is going to be t squared. The bottom term here, the 2 pi squared, is actually 2 squared and pi squared. So this is actually going to be 4 pi squared on the bottom is equal to L over G. And now finally, I just want to kick the g term over. This is a divide by g. I can now go g t squared divided by 4 pi squared. Right? And that is a expression that has been solved for L. If you have all these other variables, the g and the t, pi is just a number we can just punch in our calculator. We have our L. Again, so far I haven't really taught you the significance of these ones here. We just want to be practicing through a little bit of the algebra here. When faced with a form like this, you should be able to make a rearrangement. What we're going to do now is we're going to couple that solving with the notion of evaluating equations. So when you evaluate an equation, it's basically, I have the formula, I have the relationships between the different letters. What we're going to find is every time I have all of the numbers except for one, I can just punch in the numbers, I can use the expression as derived from you, and I can actually get the unknown number. For every equation, you can only have one unknown. So again, without getting too far in the physics, let's just try a quick practice question here. In our first chapter here, we're going to see our formula VF is equal to VI plus AT. This is eventually going to be sort of final speed, initial speed. The A stands for acceleration and time. As far as it pertains in this question here, I just want you to have the function there, take a look at the numbers that are given to you, and then just punch your way through. Let's see if we can operate on the math of it. We'll come back to the understanding bit a little bit later. So let me give you a sample word problem here. A car accelerates at 3.0 meter per second squared for 5 seconds to reach 25 meter per second. I want you to calculate the initial velocity. Right. So there's a sample of a word problem here. Usually what I try to do first is I try to draw a picture if I can. So I'm going to take my car. All my moving devices are going to be just boxes like that. So I have a car. What I'm told about my car is it actually accelerates at 3 meters per second squared. Again, we're going to talk more about acceleration in a later lesson, but for the time being here, this means you are going to increase or speed up by 3 meters per second every second. So after every second of time, you're going to be 3 meters per second faster than you were. So let's say I start from rest. Rest means you start from 0. After a second, you could be traveling at 3. After 2 seconds, you're going to be traveling at 6. You'll notice that as the speed increases, you would definitely accelerate. We're going to do this here for 5 seconds. What's measured in seconds is going to be time, so that's going to go in for a t. It's going to end up reaching 25 meters per second. In terms of your speed, I put an F for final, I put an I for initial. So this one here, notice that I'm going to end up reaching 25. So this one here is actually going to be my VF. It's going to be my final speed. The question here is my VI. How fast did the car need to be going at the beginning? Was it at rest to begin with? So that upon accelerating, so it's going to start speeding up, after every second it's going to be 3 meters per second faster than it was to begin with, and it does that for 5 seconds, so that later on it's going to be a car just heading along. It's going to be faster than it was to begin with, and it's going to be heading along actually at 25 meters per second. Just looking at the numbers here, we would expect your VI should be something less than 25, so that if I speed up at 3 after every second, I'm going to slowly build my way up to 25. So we're looking for a formula here that has some of these variables, A, T, and VF, and we're looking for VI. Perfect. The formula that I've given you is that expression here. I'm going to show you in this way here. There's actually 2 ways of doing it. Because in this question here, I'm interested in the initial velocity, you could do the practice we did earlier. We can solve our way for VI. Let's rearrange the letter so I have VI equals something, and then punch the numbers in. Or you can punch the numbers in first, and then you can solve your way for VI. I'm going to do the latter way first, just so that you can make a comparison. For all these problems, even if I know the formula, I would still copy down the formula, because this will make sure I don't miss any numbers. It'll make sure I do all the math appropriately here. In this case here, my VF, I'm going to punch in 25. I'm going to eventually hit a speed of 25. My starting speed here, I don't know. That's going to be a VI plus an acceleration here of 3 meters per second times it by 5 seconds. I'm going to just operate on these numbers here. 25 is equal to VI. 3 times 5 is equal to 15. I can just subtract that 15 over, and therefore the VI actually has to be 10 meters per second. Right? So I actually need to be going already at 10 meters per second, so that if I speed up at 3 meters per second squared for 5 seconds of time, that's the only way I'm going to reach 25. If I actually started from rest, I would actually be starting too slow. If you just give me 5 seconds, I wouldn't quite have made it up to 25. I have to initially already be moving at 10 meters per second. I mentioned here I did it without doing the solving first. Why did we practice the solving? Let's try doing the solving. So let's take the same expression here. Before you actually punch in the numbers for yourself, let's solve for VI. Because in this question here, we're interested in VI equals something. We're going to push everything that's not VI over to the opposite side. So let's just right now here, I have an A times T. It's being added. I'm going to minus A times T on both sides. So I have a VF minus A times T is equal to VI. So that gives us another lens, another way of interpreting this here. Your final speed, if you subtract off your acceleration rate and how long you accelerated for, would give you initial speed. You'll notice that the math ends up being exactly the same, which it should. We're ending with a speed of 25. We're going to accelerate at 3 meters per second for a whole 5 seconds of time. This should give you the starting speed. Again, this 3 times 5 here will end up as a 15. And then we're going to go 25 minus a 15. Similarly gives you 10. We'll talk about the rounding in a later lesson, but we're going to watch out for that we have units. So seeing as we use the exact same expression, exact same numbers, it's no real surprise that I get the same answer. Now, what's the advantage of doing sort of the second way, manipulating the variables first and then punching it in? First thing, it's nicer because it already is solved for VI. So all you're going to do is you're going to punch in VF, A, and T. And especially if there were sort of part A, B, C in this question here. For this question, I gave you A as 3 and I gave you the time as 5. What if I came back and I said, what if my acceleration is increased to 4 and I do it for 6 seconds? Or what if I increase my acceleration to 10 meters per second and I do that for 2 seconds? If there's part A, B, C, basically what I've done is I've already done the math of the isolating, moving the variables around. They can swap out the a and t, even if v final all they want. I just need to take whatever set of numbers that they give you, and I already have everything worked out. In this question, because there was no ABC, they only gave you exactly for this acceleration. This time here, it was okay for you to actually punch in the numbers first and then do the manipulation, do the algebra afterwards. So totally your call. Sometimes it is advantageous to manipulate the letters first and then dealing with the numbers, especially when we're asked multiple times for solving. Let's end off this lesson here with just one more practice. So again, we're going to come to the significance of, come to the understanding of these formulas a little bit later. I'm going to give you a slightly different formula. This is going to be VF squared is equal to VI squared plus 2AD. Right, so sort of some of the same variables here. I saw VF. Later on, it means final speed. VI is the initial speed. Again, I have the A, and this time I actually have the displacement. So let's start off with our word problem here. A plane accelerates over 100 meters at 50 meter per second squared, reaching 175 meter per second. Calculate the initial speed. So now compare it to the last question here. I'm also looking for initial speed. I'm also looking for VI. They don't always have to be giving you unknown VI, but I just wanted to give you a little bit of familiarity. Oh, if I have the time, I could actually use the formula with time in it. In this case here, my formula is slightly manipulated here. I have some of the same other variables, VF, A, and, but this time I actually have D. We're going to see with a slightly different setup, without really knowing the time, slightly different equation, but we can still do the math in operating on this number. So let's start off with the plane. Okay. Quite an artist I am. So I have a plane here. It accelerates over 100 meters. So from the start, over a sort of a launching pad here, the displacement that it travels here is actually 100 meters. It's going to accelerate at 50 meter per second squared. Again, what that means here is at 0 seconds, it would be at 0 seconds. At 0 seconds is at VI. I don't know what it is, but at 1 second, it would now be 50 faster than VI. At 2 seconds, it's going to now be another 50 after VI. So basically, every second that it travels over, it's actually going to be 50 higher than it was to begin with. It's going to end up reaching 175. Is this one here a VF or a VI? Upon reaching 175, it means this one here is actually a final speed. So when the plane gets over to be here, the V final, the VF, is actually going to be 175. Sometimes you can actually figure out what each number is just by looking at the units. I can say, well, what's measured in meters? Well, meters here should be a distance. That's going to go in where I say D. In this case here, meter per second squared. We're going to slowly get more familiar with that. That meter per second squared combination is actually a combination for acceleration. So that's going to be A. So let's just try off here. We have our formula. VF squared is equal to VI squared plus 2AD. I'll know I can use this formula. So far I have 4 variables. One equation can only deal with one unknown at a time. So I can just slowly work my way through here, and I can solve for the one missing variable. So let's try it through here. My VF this time is going to be 175. This time they want you to take 175 and square it. That's why it's the advantage of actually having the expression right above you, so you can actually punch in the numbers. You won't forget to do any operations. The VI I don't know yet. I need to do the square. Plus twice the acceleration here of 50, and it accelerates over 100. You'll notice in this formulation, I don't actually need the time at all. So you can use a calculator, either scientific or graphing, both are fine. 175, do a square. So this gives you here 30625 is equal to VI squared. I'm just going to punch in all this stuff here. 2 times 50 times 100 gives you 10,000. I'm going to subtract the 10,000 to the left-hand side. So your VI squared is equal to 20625. Now that looks like a really fast speed. That's not VI. That's VI when it's multiplied by itself. If I want to get rid of the square, I need to take the square root of it. Root of 20625 gives me here 144 meter per second. And again, unlike where we may have assumed, oh, maybe I'm starting at rest. No, in this case here, I actually had to be going some speed to begin with, because you only give me 100 meters worth of runway, I'm going to cover that distance in no time at all. And if I cover that distance in such a short time period, I really am not going to be able to increase speed by that much. I actually need it to be a VF already 144. If you give me 100 meters of runway, I only can accelerate upwards of 175. It's not even 50 more than it was to begin with, so I haven't even taken a second to actually travel the speed here. If you like, when you actually find this variable here, you can actually punch into other equations. You can actually solve for other variables. In fact, sort of the more numbers that you know, you have more freedom to actually deal with other equations as well. Let's just back up here and let's just use the equation we did from earlier. VF is equal to VI plus AT. What if I was interested in, say I started my clock when the plane steps on the pedals and starts accelerating. How long did it take? I'm expecting it's going to be less than 1 second, because in 1 second I would expect it to be 50 higher. 144 and 175 are not even 50 yet. But in this case here, now I know what the VF is. I can say, okay, if my VF is 144, my VF is 175. If my VI, my initial speed, what I just calculated, is 144. That's why it helps having your formula there. The acceleration rate was 50. Let's solve our way for t. Again, you'll notice what I'm doing here is I'm actually punching the numbers in first because they're not swapping out the numbers. Oh, part B of the question, what if the VI was this and A was this? They're just asking for the time for this exact problem. So I punch in the numbers. I'm going to manipulate my numbers, push my numbers around just once, and solve my way for t. First thing I need to drag over is the 144. Right now it's a plus 144. Let's go 175 minus 144. That gives you 31 is equal to 50 times t. And therefore t is equal to 31. Right now multiply by 50 needs to get rid of by divide by 50. When you divide it, it gives me here the time was actually 0.62 seconds. Don't worry too much about the rounding. At this point here, we'll come back in a later lesson to do that. I just wanted to just start introducing to you, if you're given a function, how can we solve and manipulate through and actually evaluate so actually we get a reasonable number. So your worksheet will have more practice with this, just manipulating letters around, punching numbers in to evaluate. Just let me know if you have any questions. Thanks, guys. Take care.